Hello, everybody. My name is Bakir Akbar Ali, and I'm going to present a paper named Variational Implicit Processes, which is done by a group of researchers at the University of Cambridge. And the paper was published at ICML in 2019. So, all right, let's start with the introduction. So, in Bayesian machine learning, the big idea is that we place a prior over functions and then we update that prior using data. This gives us what is called the posterior. And why do we do all of this? Because the Bayesian models give us uncertainty estimates. They help us avoid overfitting and they allow us to reason well when even we have limited data. The classical tool for this is Gaussian processes. GPs are very good when the goal is to model distributions over functions, but there is a catch. GPs rely on a kernel to describe how inputs are related, and the kernel is usually hand designed, often very simple, and it limits how expressive the GP can be. So the main takeaway here is GPs lack expressive power. Neural networks, on the other hand, are incredibly expressive function approximators. So a very natural idea is let's use neural networks as priors over functions instead of relying on simple GP kernels. If a neural network has random weights, then before seeing any data, it naturally generates random functions, and there is uncertainty in those functions. Bayesian neural networks try to do exactly this by placing uncertainty over the weights, but this leads to a major problem. The weight space is extremely high dimensional and there's a lot of redundancy, and the posterior overweights becomes extremely hard to approximate. So Bayesian neural networks struggle because they operate directly in weight space. And that leads us to the key idea of the paper. Instead of doing inference in weight space, the authors propose to do inference in function space. What does that mean? It means we treat the neural network as a function generator, and that generator defines something called an implicit process or IP. So instead of inferring weights, we infer functions, and this gives better uncertainty and avoids the entire weight space mess. So what exactly is an implicit process? An IP is a distribution over functions, but instead of being defined by an analytic kernel like in Gaussian process, it is defined by a sampling procedure. We start with a latent random variable z, which belongs to some probability density function, and we pass it through a deterministic mapping, which is basically our neural network. So for each sample z, the neural network outputs a different function. That's why we call it an implicit process. The distribution exists, but we can only sample from it, not write down its density. And here is the simplest example. Let's say z or theta comes from a normal distribution, and then f of x is just a neural network with those parameters. And then the neural network automatically defines an implicit process. We don't need a kernel, we don't need a closed form probability density. We simply sample a value of z and evaluate the network. and that gives us a function. So implicit processes are not limited to just simple neural networks. And the paper shows examples like neural samplers, warp GPs, Bayesian neural networks, and Bayesian RNNs like LSTMs. All of these can be viewed as implicit processes because they produce functions by sampling some latent variables and running them through a generator. So this picture is actually taken from the paper itself. And why IPs are useful? Now, now, so why are IPs useful? GP kernels are hand designed and pretty limited. Implicit processes allow any generator. So, for example, a neural network gives flexible function shapes. A CNN gives spatially structured functions. An LSTM gives functions over sequences. Even physics simulators can be used as generators. So the space of possible function shapes becomes much richer than what you get from a standard GP kernel. Now, let's talk about variational implicit processes. We start with our implicit process. And so here's the notation as you can see, and why and observations that we indicate as y, and f of x plus error. And our goal is to infer what functions f are likely given the data. But here is the problem. The implicit process has no density formula, so we cannot compute the posterior, and we also cannot compute the marginal likelihood. So the solution must be some kind of approximate inference. And in the next slide, we talk about the trick that the authors have proposed. The trick is simple but quite effective. We approximate the posterior over functions using a Gaussian process. So why do we use a Gaussian process? Because a GP or Gaussian process is also a distribution over functions, and GP's posterior is tractable, and we can fit a GP to any function behavior we observe. So instead of dealing with the intractable implicit process posterior, we replace it with a GP posterior. Now let's look at how they actually make this work. They use a version of the wake-sleep algorithm. First, the sleep phase. We first sample a latent variable z, and we use it to generate a function f of x, evaluate it on some input points, and add noise to produce synthetic outputs, and fit a GP to the synthetic data. So the GP is forced to learn how the implicit process behaves. Basically, the GP learns to imitate the IP. Then the wake phase. In the wake phase, we take the GP's posterior, which is tractable, and use it to approximate the IP's posterior and compute the variational objective log. And then we optimize this with respect to theta. So overall, in the sleep phase, the GP learns from the IP, and in the wake phase, the IP learns from the GP. This alternating process is what they call the variational wake sleep. And so to summarize, to wrap it up, implicit processes are powerful, but their posterior is intractable. VIP solves this by approximating the function posterior with a tractable GP. In the sleep phase, we generate fake functions from the implicit process and feed a GP to mimic them. And in the wake phase, we use the GP's posterior to optimize the parameters of the implicit process on real data. The final result is scalable Bayesian inference in function space, which better with better uncertainty estimates than Bayesian neural networks and much more flexibility compared to Gaussian processes because of the diversity of the neural networks as prior. So thank you for your attention. Thanks for listening.